has done his BTech as well as his PhD from IIT Delhi, and he was a postdoc at the Max Planck Institute. And he has been in faculty at IIT Delhi since 1998. He works primarily in DA, which is design and analysis of algorithms, for NP-hard combinatorial optimization problems arising in network design, scheduling, routing, facility location, etc. We have already had a... Sorry about the disturbance. So you've already encountered facility location earlier in the summer school, and he also works on that. He is a fellow of the Indian Academy of Sciences, Bangalore, and was awarded the SS Bhatnagar Award for Maths in 2016. Today, Professor Naveen Garg is going to talk on multi-cut. So with that, I'll welcome him to the stage.
Thank you. I think I just turned this off. Students? Okay, good. So, never mind. So, we'll talk about. Oh, do not cross. He crossed it, sir. If at the end you can't see this, you can either come to the front or you can let me know and I'll write bigger. Yeah? Okay, so before I tell you multi-cut, I can tell you what multi-commodity flow is. Oh.
You have to erase this.
Have to erase this?
Yeah, because it won't record there.
Ah.
Sorry.
This is the line I should not cross. Good, let's.
We won't see.
Thanks. Okay, so as I said, I'm going to be talking about multi-cut, and before I talk about multi-cut, I have to tell you what multi-commodity flows are. And before I tell you about multi-commodity flows, I will briefly recap flows in graphs, right? So what is the setting? The setting is that you're given a graph. Let's assume directed graphs for explaining flows. But when I'm talking of multi-cut and multi-commodity flows, I'll talk of undirected graphs. It's an easy extension, so don't worry too much about it. Where every edge has a capacity, a non-negative capacity. And usually we are talking of a source and a sink, so S and T. So S and T are two vertices, given vertices. So this is my graph, this is the source, this is the sink. Every edge has a capacity associated with it. And what is a flow? A flow is another function on the edges. Okay? And what properties does it satisfy? It satisfies two properties. One is called capacity constraint. What do you think that means? What do you think capacity constraint should mean, right? Capacity means that edge can support at most that much amount of flow, right? Okay, so intuitively think of this as a network of pipes, okay? And there is a tap, open tap here, which is sending in a large amount of water, and there is a sink, right, from where water can go out. And think of these capacities as the diameter of the pipes, right? So if an edge has large capacity, that means that's very fat pipe. Okay? And what you want to determine is how much flow you can send from here to here. So you're thinking of flow as a continuous, in time, right? So, so that's why we are thinking of it as a function like this. And capacity constraint now is they're saying that for all edges in this graph, f of e is less than c of e. Right? The flow on their edges is the capacity of the edge. right? So you can think of it as a network of pipes. You can also think of it as a road network, right? And then what do you think capacity should represent?
Traffic per number of vehicles it can accommodate.
Number of vehicles it can accommodate, let's say per unit time, right? So if it's a wide road, then the number of vehicles that can go across that point in time is much larger. If it's a narrow road, it's correspondingly less, right? And in a traffic network, you are, let's say, trying to determine how many people, how many cars can you route from one particular source, let's say IISc campus, to, you had your IPL yesterday, right? So whatever, Chinnaswamy Stadium, right? So how many cars can go from here to Chinnappa or Chinnaswamy? Chinnaswamy, okay, good. How many cars can go there? Yeah? Or what's the flow? So that's capacity constraint. What do you think should the second constraint be? Right? Can I just give any value of flows to the edges? No? Why not?
Flow inside, coming inside a vertex should also be the.
Okay, so there should be some kind of conservation, right? Otherwise it will not make sense, right? Cars will get generated at intersections, right? You don't want that to happen. Conservation, right? So for all vertices other than S and T. At S and T there is no conservation, right? New stuff is coming in, at T stuff is going out. Summation Fe, E belonging to delta in V equals summation Fe, E belonging to delta out V. What is delta in and delta out? Well, you can imagine what it is, right? This is a vertex V, this is the set of edges coming in, so this is the set delta in, this is the set of edges going out, so that's delta out. Okay? So incoming flow should be equal to the outgoing flow. And what's the biggest result in this domain? Okay, before that I should tell you what a cut is, right? So this is what a flow is, and usually the objective, as I said, is to maximize the amount of flow you can send from this, right? So such a flow function would be called a max flow. Maximizity of these edges that are going from this S side to the T side, right? Let me sum up the capacities. Maybe this is 3, 2, 5, 6, 7. Maybe there is an edge like here going 10, but I'm not going to count this edge. So it's only 3 plus 2 plus 5 plus 6 plus 7. That I will call the capacity of this particular cut. So capacity of this cut S comma T. Yes? Why am I telling you this? Why do you think I'm telling you what the capacity of a cut is? I see. Masti ke liye. Why do you think this is important? That's how much flow you can push through. Can I always push this 3 plus 2 plus 5 plus 6 plus 7 across? No. This is the maximum, exactly. This is the upper bound, right? The amount of flow, no matter what you do, the amount of flow you can send from S to T cannot exceed the capacity of any cut, any ST cut. Such cuts are also called ST cuts. Why ST cuts? Because they are separating S and T, right? So maximum ST flow is always less than capacity of any ST cut, right? She just proved it. It's clear, right? It cannot happen. And so the big theorem is that, so this is also true when this is the minimum capacity ST cut. If I look at all possible ST cuts and I take the one which has the smallest capacity, right? This statement is also true then, right? But then, if I take the minimum ST cut, this becomes an equality. You can actually send a flow equal to the capacity of the minimum ST cut. Right? That should be a surprising statement, right? That you can always push a flow equal to the smallest possible ST cut that there exists. Okay? So this is called the max flow min cut theorem, and this was actually instrumental in setting up an entire area of operations research. Right? This was the fundamental theorem that started this whole domain of optimization, not optimization per se, but operations research definitely. Right? And this is due to Ford and Fulkerson from 1956. Okay? Good. So actually, you're in a school on approximation algorithms, right? So you should understand that one of the key goals in approximation algorithms is the idea of, or actually when you're talking of NP hard problems itself, is this idea of certificates, right? If I have to convince you of the correctness or the of a certain statement or of a certain claim, then I should be able to prove that to you, right? If I have to convince you that the maximum flow in a network is 10 units, how do you think I can convince you about this statement? Give a cut of capacity 10. Is that all that's needed?
No other cut should be there to have capacity more than 10.
Sorry?
No other cut should be there so that its capacity is more than 10.
How will I convince you that there is no other cut about that? Right? How many cuts are there? How many ST cuts are there in the graph? Exponentially many, right? So when we talk of certificates, we talk of small certificates, something that you can quickly check, right? So we cannot talk of, oh, tum sare cuts crack ke check karo. No, that's a waste of time, right? Or you cannot do that. Forget waste of time. But that's not the point at all, right? So what he's saying is right. I show a cut of capacity 10, but that doesn't convince me that max flow is 10. It just says that max flow cannot be more than 10. But how do I convince you that the max flow is 10? She was saying, find a path
that has a flow of 10.
that can support a flow of 10. What do you mean a path has a flow of 10? That can find one path जिस पे total flow जो हम भेज सकें वो 10 units का भेज सकें. But flow is not just flow on a path, by the way. Maybe I should have done an example. So suppose simple network S, T, 2, 3, 4, 5, 6. Okay, who can tell me what's the maximum flow that can go from S to T? Huh? 7? 6? 5 भी? 6? ये तो बहुत जल्दी आप लोग कंफ्यूज हो गए. I was hoping कि थोड़ी और लेट में कंफ्यूज करूंगा मैं आपको. 6. Okay. Why 6? Okay. This cut, इसकी कैपेसिटी कितनी है? Going from the S side to the T side. S side to the T side. 6 है. तो 6 से तो ज़्यादा फ्लो जा ही नहीं सकता, कुछ भी कर लो. और 6 यूनिट्स का जा सकता है. उसके लिए क्या करना पड़ेगा मुझे? We are coming back to the same question earlier, right? 6 यूनिट्स का दिखाने के लिए मुझे क्या करना पड़ेगा?
So we have to show a flow of 6 and have a cut of
Exactly. We have to show a flow of 6. And what's a flow? A flow is a function of the edges. तो हर edge पे मुझे बैठ के एक नंबर डालना पड़ेगा, which is the flow. Right? तो इस edge पे मैं 2 units of flow भेजूंगा. वो कहाँ यहाँ जाके उसको कहीं तो जाना पड़ेगा, तो उसको यहाँ भेज देते हैं. ठीक है? फिर ये यहाँ पे 5, देखो 4 ही भेजना है, 6 ही भेजना है, तो 4 और भेजना है. तो I send 4 here, and then this remaining 4 it goes here. So simple. Yeah? This is carrying 6 units of flow. You understand? It's not on one path. It could be on many paths. These paths need not be disjoint either, as in this example. They could be sharing edges and so on. Okay. So, maximum ST flow, min capacity of any ST cut. Maximum min cut, maximum flow equals minimum cut in a graph. Okay. So, traffic doesn't just go from one place to another. Right? It goes from many places to many other places. Yes? Or this is not just road traffic we are talking of, we are also talking of internet traffic. Right? There will be many sources in the network, there will be many destinations. Right? And so that brings us to the setting of multi-commodity flows. Okay, so I'll start making changes to here. So I'll say S1T1, S2T2, S3T3, and so on. Many pairs, right? Maybe SKTK also. K pairs. So you have a graph. Now we'll assume graph is undirected. Okay? So we'll make this undirected. Okay? And what? Okay, so now can you tell me what the capacity constraint should be? What should be that? So, okay, so now what are we talking of? We are talking of traffic going from S1 to T1, right? Maybe IISc से जो सारी cars जा रही हैं, they want to go to where? Kalakshetra for some, is there a Kalakshetra here or something like that, right? I went to a concert yesterday, Subramanian concert at Chowdi Hall. Maybe all of you also went there, right? So maybe there is traffic going from here to Chowdi Hall, right? And somewhere else, right? Maybe people in Whitefield are all going partying somewhere else, right? So some party place there. So there could be different sources and corresponding destinations, right? And there could be traffic corresponding to them that you want to send in the network. So, kaise, how should I modify the constraints? What should the multi-commodity flow problem become? What should the capacity constraints be?
Summation Fi,
F?
Fi, like can we classify
The flows? ये तुमने देखा क्या पहले सब? नहीं ना, ठीक है, then it's good. Okay, so good, very good. So what she's saying is, it's perfectly right, right? अब we should be thinking of a different commodity, right? For every sourcing pair, we should think of one commodity associated, right? That's where the term multi-commodity comes from, and I'll write that down. Associate a commodity with each pair. Right? So if you want to think of that pipe example, think of it as कि milk भी flow हो रहा है network में और जो है water भी flow हो रहा है, and these are immiscible commodities, right? They don't mix with each other, right? And then you want that. What do you want? You want that the total flow. I'll use a different color so that you know. Let's say Fi. So F. So now we want Fi. So now my multi-commodity flow is specified by giving the flow of every commodity on every edge. Yes, that's how multi-commodity flow will be specified. So Fi is the flow of commodity I on a certain edge. And now what do I want? I want that, is this constraint correct? That the flow of the ith commodity is less than the capacity of the edge? Is that what we want? Huh? Summation, very good. Right, sum over all I. Going from 1 through k. The total flow of all commodities put together should be less than the capacity of k. Right? That's the obvious thing to do. Right? How should this constraint change? Conservation. What do you want to conserve? Each commodity. As I said, you can't convert milk to water, right? Or vice versa. So for all I, you want this to be true, and conservation at all nodes except S, the source and the sink for that commodity. Right. So now what is in and out? What is in and out? Right. So total flow. So we'll still have the notion of flow coming into a vertex and going out of a vertex, but we will not associate a direction per se with an edge, right? So an edge can be used in either direction, right? Which makes sense in a road network. It could be used in either direction, right? We just want that the total flow, whether it is being used in this direction or in this direction, should not exceed the capacity of the direction.
Are there any edges between S1 and S2?
There could be. Right? But the flow has to go from S1 to T1 and S2 to T2 and so on.
Can S1 and S2 be same?
Yes, they can be sustained.
So the direction of the flow is now specified in the flow function, is this?
The direction of the flow will get specified. Yeah, maybe that would be the right way to do it. Yeah. So, okay. So Nildara has very valid questions. And that should also be coming to your mind, given that I said this graph is undirected. So I can sort of make it okay by replacing every undirected edge by two directed edges of the same capacity. Like iski capacity 3 thi, so I put 3 and 3. And then but the total flow over these two edges put together should not exceed 3, not 6. Should not exceed 3, right? So This would be one way of thinking of it, that you actually associate a direction and then all this business of incoming and outgoing can be taken care of properly. But then here you should be saying sum over all edges. So I should have E and E reversed both summed. Yeah? So minus the technical thing. Yeah.
So what if there is a case where we have a component S and a component T, and the starting points will lie in component S?
All starting points in S.
Yeah.
All starting points in T.
Yeah.
All ending points in T.
Yeah, and they both are connected by a cut edge.
They both are connected by a cut edge.
Single edge.
A single edge. So
So in such case, can we include that edge in multiple commodities or like?
See, देखो एक edge के through I think what he's trying to say is something like कि S1 T1, S2 T2, S3 T3. Yeah, you want to say something like this? बिल्कुल हो सकता है. इसकी मान लीजिए कैपेसिटी 3 थी, इसकी 7 थी, इसकी 2 थी, इसकी 4 थी, इसकी 6 थी, 5, 4. So I could be sending flow like that. Let's say 2 units of flow like that, and maybe S2 to T2 जाना चाहिए था. Some of other maybe 4 units of flow like that, and some other flow like that. That can happen. Right? The whole point is that the edge. Think of traffic, right? Now color your cars based on the source and the destination. Yes, so that they are different commodities. You know, one is red set of cars, one is blue set of cars, one is green set of cars, and they are all using the same highway. Yeah.
So if there is an edge between S1 and S2, so how do you say whether some commodity starting from S1 or S2? Because if S1 and S2 are connected,
Yeah, there is an edge between them.
yeah. So
Okay.
and if flow is going from S1 to S2 and then it's going to somewhere else,
Right.
then like you can equivalent write it as okay, just remove that edge between S1 and S2, and now like you are just pumping more out from S2 now.
See, it's very important that the destination, right? So that's why I'm calling this commodity. So I could have a network which looks like this. Let's say, and T2, and let's say capacities are all 1. Okay? And I wanted to send 1 unit of flow. Okay? So now I'm telling you about demands. So suppose okay, what's the objective here? There could be multiple objectives. One could be maximize the total flow we are sending, right? But there could also be an objective which say, for commodity 1, I want to send D1 units of flow. For commodity 2, I want to send D2 units of flow, and so on and on. So suppose here I say that between S2 T2, I want to send 1 unit of flow, and between S1 T1, I want to send another 1 unit of flow. Can you tell me how you would do this in this network? And that should also sort of clear some of the questions that you are asking me. कर सकते हैं? Do you think this can be done in this network? No? Okay, so these are undirected edges. These are directed edges, right? So then, okay, so let me make them undirected. Can you do it now? Yes? Who said yes? Why?
You can take the upper right corner path,
Yeah?
and you can take the lower left path.
Okay? And? No, but you also have to send S1 and T1 flow. See, you have to send 1 unit of S2, S1 T1, commodity 1, and 1 unit of commodity 2. You are almost there. And all capacities are 1. How will you do that?
So you go H2 to P2 by clockwise and S1 to P1.
Yes, sir.
Sorry?
H2 to P2.
All capacities are 1. You are saying S2 to T2, you want to go clockwise.
Yeah.
And S1 to T1, you want to go anti-clockwise. But then this edge will be violated if you are sending 1 unit of flow.
But this is bidirectional, right?
No, total capacity is 1. Okay, so don't, so total amount of flow that can go through that edge is 1. In either direction, in both directions put together, not in either.
So, similar to the structure you just created, half goes from
Very
S1
good.
to
Half is the key. When you said half, it's clear already. Right? So you send half like this,
And similarly half from S1.
And you send half like that. Right? There is no other way to do this. And this is that.
By the way, can we make it single source? So all the sources you connect to one source and then.
Oh, if you just make it singles, you're given all of this, and then you just combine these sources into one, and then what do you want to do? Then you want to solve it as a single source.
No, you add one source, and then outgoing edges from that source to S1, S2.
Okay, natural question. So ये कह रहे हैं कि क्यों इतना ये SIs हैं S1, S2, S3, S4 और ये मेरे T1 हैं T2, T इनको जो है let's just connect them to one super source and let's connect all of these to one super sink and let's compute ST flow. What's the problem? Who will tell me?
Capacities of the new edges.
Capacities of the new edges. Infinity डाल दो, कोई फर्क नहीं पड़ता. Suppose the objective was to send maximum amount of flow in the network, then I could just put infinite capacity edges.
You are not differentiating between the commodities.
You are not differentiating. Very good. So there could be flow that is going from here and then it goes to T2. Right? What flow is this? Commodity 1, commodity 2. S1 से आप flow T2 भेज रहे हो. This should not be allowed, right? S1 से तो T1 ही जाना है flow. Right? आपको जाना था स्टेडियम, आप चले गए मंदिर. That doesn't make any sense. ठीक है? So these have to be done separately. Sorry?
In the combined setting, the conservation constraints
Yeah.
were not fine-grained. I mean, this issue is happening.
No, you could still keep this. You could still keep this.
But you're not tracking.
But you will not be able to. Yeah. So what is it that prevents you from sending the flow that came out of here into here? Even if it is conservation. Yeah, this flow could still find a way because there is nothing that is distinguishing. The conservation is in some sense, but
But then this pathway can legitimately happen even without the super source and the super source.
this pathway, no, no, because conservation would also be at this. So
So I meant that I think when you outsource it to the standard flow problem, you're forced to do, and you don't see the FIs anymore.
you can actually get rid of the FIs also.
I mean, you would have to if you want to use for I mean, I guess the traditional algorithm only allows you to specify one conservation constraint. And that's what it means to lose the distinction is what I thought it was.
No, I think even if you were to keep these constraints, even then you would face the challenge.
4% will be able to.
I could solve a linear program and formulate this in that manner.
Alright, so I see. So then I was wondering, because that blue path from S1 to T2 still exists in the graph without the super source and the super sink. So
I think we're missing the constraint that from SI, whatever is going on from SI has to end up in
Has to end up at TI because there is conservation at all other places for that commodity. Right? So the only place where it can get killed is at TI and nowhere else.
right. So I think that's probably why maybe it's a language thing. But what I meant was the conservation constraints are what are ensuring that the commodity.
Yes. Cool. Okay. So now question is obviously. So suppose we are going to consider in this lecture, I am only going to consider the maximization version of multi-commodity flow. Maximize sum of flows of all commodities. So that's called the maximization version. And now the obvious question would be, is there a corresponding relation? Right? I want to find the maximum flow that I can send from S1 to T1, S2 to T2, some of these. Now can I say something like the maximum amount of flow I can send is equal to the minimum cut separating this? Now what does that mean? What is the minimum cut separating S1, T1, S2, T2 and so on? How should one define it? Okay, I'll start erasing some stuff now. Hopefully it's all gone into your head by now. Yeah.
Previously, the flow of the graph was the net flow coming out of S.
Yes.
That's the thing we are maximizing. And
Yeah.
now this is the net flow coming out of the SI plus sum.
Yes, that is what you're maximizing. Yeah. Okay, so what's a set of edges whose removal separates each SI from corresponding TI. That we'll call it a multi-cut. That's a multi-cut. Okay? Okay, let's take a simple example. And this example will be there with us for some time. S1 T1, S2 T2, S3 T3. All capacity is 1. Okay? Who can tell me what's the maximum amount of flow I can send between these pairs? Very simple graph, right? Just a tree. Any of the two edges? No. Abhi, I'm asking about flow. What's the maximum amount of flow I can send between these pairs in this graph? In total, yeah, sum. We are maximizing the sum of the flows we can send. 1, 3 by 2. Start thinking in terms of halves now, or fractions, right? 3 by 2. कैसे भेजेंगे? Everyone can see 3 by 2? Well, actually, once I tell you it's 3 by 2, it should be straightforward. S1, this is flow of commodity 2, blue, yeah? And let's use green for S3 T3, and let's use red for, yes, and a half unit of each one of them. You can see that conservation is maintained and capacity is also met. Right? So maximum flow is 3 by 2. Okay. Now what's a multi-cut? What's a set of edges whose removal will separate every pair? Huh? Of course, if you remove all, then everything gets separated. But what's the smallest set? Any 2. Right? So that's a multi-cut. Right? So now I can tell you what the capacity of a multi-cut is. The capacity of a multi-cut is equal to sum of capacities of edges in the multi-cut. Right? Nothing new there. And so it should be clear that maximum multi-commodity flow is less than or equal to capacity of any multi-cut. Yes? Why? Because the multi-cut acts as a bottleneck. Right? अगर कुछ edges हैं, if there are some edges whose removal can disconnect every pair, then every flow between the S1 and the T1 has to go over those edges. If it has to go over those edges, then the total capacity of these edges उससे ज़्यादा flow की value नहीं हो सकती. Right? So this statement should be obvious. And since it is any multi-cut, it's also true for minimum multi-cut. Yeah? So it's obvious that the maximum flow is less than or equal to the minimum multi-cut in a graph. Right? I'm drawing parallels with what we did for single commodity. Is there equality? And you've already seen that there is no equality from this example. Right? So this remains an inequality. And in this example, the maximum flow is, max flow is 3/2, and minimum multi-cut is 2. Okay? Questions? Okay.
Excuse me.
Yeah.
So in the single to single sync version, you could show that you couldn't do better than a max flow. You could certify you cannot do better by showing a min cut.
Yeah.
Here, for this example, you can show you cannot do better because each edge is being used.
Yeah.
But
each edge is being used.
Complete to the max capacity here.
Okay, that's not a, I would not be satisfied with that argument.
So in general, for a multi-cut, how would you prove that this is a maximum?
Okay, how would you prove that this flow is the maximum possible flow?
Yes.
Yes?
Well, if that is not an equality,
yeah.
So you will need a proof to show that this flow is in fact maximum.
Okay, we'll come to that. We'll show how can one argue that a certain flow is the maximum possible, right? And there, okay, let's do that first then. Okay, so I want you to formulate this problem as a linear program. Okay, which problem? This maximum multi-commodity problem. किसको याद है linear program जो नील तरह ने सिखाया था आप लोग को? सबको याद है? Good. So what will we have? So this is my graph. We have S1 T1, S2 T2, S3 T3, and so on. Let me denote by script P1 set of paths from a script Pi from Si to Ti. All possible paths. Paths are there. कोई बात नहीं. ठीक है? All possible paths that are there from Si to Ti. Let's use that. And now I'll have f of p is going to be my variable. F of p is the flow I send, flow along path p. So clearly the flow that I send along any path is non-negative. With this variable and this definition, who can tell me what should my constraints be?
So this would be an example of how you decompose a flow into paths.
Yeah. I'm doing a formulation using path variables, which you might say is not a small formulation because the number of paths is huge, right? And so I'm actually having a number of variables which is exponentially large. But for the purposes of this class, right, because we are not actually solving this linear program, there is a different linear program that you can solve, which will be more efficient. But for the purposes of this class, this will suffice. Okay, so who can tell me what I should write?
What is the flow? What does it mean, flow along the path?
Flow along the path, this example. What's the flow along this path? Half a unit.
Like some of the edges could have more flow than.
Maybe. When I say flow along a path, I mean, yeah, good. So, you are right. So, I should have told you about flow decomposition. So, 2, 3, 3, oh, no. 3, 2, 1. Okay. So let's say this is the flow, the single commodity की बात करें. This is the flow from S1 to T1 or S to T. Not the capacity, this is the flow. Right? This meets the capacity. Now, one way of thinking of flow was, okay, you can see the edges. Okay, let's give these the direction to the edges, the direction to the flow. And you can see that conservation is happening, right? 2 plus 1 equals 3. Oh, sorry. My bad. This should be 4. Yeah? And 3 plus 1 equals 4. Yeah? There is another way of thinking of this flow, and that's what's called the path decomposition. I think of it as 2 units went like that. Right? It's not that every edge on this path is carrying 2 units of flow. Some are carrying 2, some. But 2 units went like that. 1 unit went like that. And 3 units went like that. Right? Again, take the example of your cars that are going. The flow is the total number, the aggregate number of cars. But these were physical cars that were going from here to there. So I can talk of how many cars followed this path, right, from IISc to the stadium. Yeah? This can always be done. right? Given any flow function on the edges, I can always decompose it into a small number of paths, in fact, into only m paths, right? And I can talk of the flow along a path.
Basically, it will be the minimum of the flows on any edge in that path.
Not necessarily. Not necessarily. Would it always be the minimum? Right? So when you are, okay, so what you are saying is, you could think of it as the following. You took a path and you took the minimum flow on any edge, and you, for that path, you assign that flow value, and then you decrease the flow on every edge of that path by that amount, because you have other steps to do, right? And then you repeated it, right? Which is why it might not always remain the minimum, is what I'm saying. Okay, and in fact that's a procedure, and you can argue that you can always do a decomposition in m paths only, right? So that's called, for future reference, that's called flow decomposition, right? And the same thing can be done in multi-commodity flows, right? So here, instead of saying this edge carries half a unit of commodity, what was that? Commodity 2, and this edge carries, so this edge carries half a unit of commodity 2 and half a unit of commodity 1. I'm saying that the flow is happening in this manner. Okay, I need to speed up a bit. Okay, good. So coming back to this linear program, important that we formulate it now. Who will tell me? So now you understand how much flow, what it means for flow to go along a path. What should the constraints be? What should the objective be?
For all paths, maximize FP.
Okay, you have to tell me what the objective is. So maximize summation f of p, p belong to union of pi. Yes? Over all paths, over all the right, over all the SITI, just do the sum. F I of p, no. So why did I not put an I there? Because p is going from a certain source to a certain destination. Yes? So I'm just thinking of it as it's carrying the commodity I. What else should I have? Okay, so conservation. कौन बताएगा कि मैं, sorry नहीं, conservation यहाँ automatically हो रहा है, because I'm sending flow along paths and not along edges. Yeah, or thinking of it as that. So capacity कैसे मुझे formulate करना चाहिए? Let me do it for you. So summation f of p. So if I take any edge in this graph, then summation fp summed over all p. So I will take any edge in the graph and I look at all the paths that go through this edge and look at all the flow values on this path. There's some p such that E belongs to p. Yes? ये sum कितना होना चाहिए? C. Capacity of the touch atoms. And that's it. This is the entire linear program. Right? क्योंकि आपको केवल कैपेसिटी कंस्ट्रेंट मीट करनी है. कंजर्वेशन आपका ऑलरेडी हो रहा है. क्यों हो रहा है? किसी भी नोड पर किसी भी कमोडिटी का इनकमिंग फ्लो विल बी आउटगोइंग, बिकॉज हमने फ्लोज को पाथ्स के साथ एसोसिएट किया. तो जो पाथ्स इसके थ्रू जा रहे होंगे वो जितना फ्लो अंदर लेके आएंगे उतना ही फ्लो वो बाहर लेके चले जाएंगे. इजी. Questions? Okay, cool. So this is a simple linear program.
The motivation is that this is already hard for people.
Which the cut is hard, finding the flow is easy. Finding integral flow is hard. Okay? So now let's write the dual for this. हाँ, अब पता चलेगा ना? कैसे लिखते हैं dual?
You have one dual variable for each of the constraints.
You will have one dual variable for every constraint. So there are only these kind of constraints. Every edge के लिए there is one constraint, right? तो इसके लिए हमने एक dual variable रख दिया L of p, length of this edge. Okay? And now what should the objective be? आप सब लोग फटाफट objective बता सकते हैं मुझे, I think.
Summation of LE times C.
Minimize summation over all edges LE times C. This is easy. Harder part is writing the constraint. Now tell me what the constraint is for this dual. Remember, you have to take the variables here. So what is the variable here? It's the flow along a path. So you have to look at a certain path, right? And वो path किन constraints में appear होगा? हाँ? अगर ये मेरा path है, so all the edges that are there on this path, it will appear in the constraints corresponding to those edges. Yes? And what's the coefficient? 1. So this will just be summation LE. I'll be just taking the dual variable for that edge, multiplying it by the coefficient which is 1. So summation LE, E belonging to the path P. This should be what? Greater than or equal to the coefficient of that variable here, which is 1. So this should be greater than or equal to 1. And this is written for all paths P in the collection capital P. Okay. Let me use P to denote union of Pi. What is it saying? Saying something very simple. Saying, give some lengths to the edges. Right? Such that for every path in my collection script P, the length of the path is at least a 1. What does that mean? Your collection of paths is all possible paths between S1, T1, S2, T2, S3, T3 and so on. So what is this length function telling us? It should be connected. What should be connected? The graph? नहीं, connected तो देखो मतलब graph जो हमें given है, you can assume that it is all connected and everything, right? What is this constraint saying? Think about it for a minute. Forget about the objective for now. What is the constraint telling you?
So between SI, there will be a cut.
No cut what? So between Si and Ti, if I take any path, what is the length of the path under this length function? At least 1. Can there be a path between Si and Ti which is less than 1? Any path? Can there be any path which is less than 1? If I look at this length function? No, because I look at all possible paths between Si and Ti. And every path has to have a length of 1. So what does that mean? That means the shortest path between Si and Ti is of length at least 1. Right? That's how you can interpret this. Right? So, simple interpretation, assign lengths to edges of G such that shortest path between any Si-Ti pair is at least 1. Of course, you can say, हर edge को मैं 1 length दे देता हूँ, क्या टेंशन है? हर पेड़ के बीच का shortest path 1 हो जाएगा कम से कम. Minimize. What are we trying to minimize? We are trying to minimize this quantity. What does this tell us? किन edges पे हमें लंबी length देनी चाहिए? GT capacity कम हो. Yes? By the way, this is also true for single commodity flow. Yes? मतलब ये multiple commodities के लिए, K more than 1 है, but single commodity के लिए भी ये true है. Right? अगर मैं linear program लिखता, single commodity के लिए और dual लिखता, तो exactly यही होता. वहाँ पे हम क्या करते हैं? वहाँ पे हमारा जो single commodity है, ये S1 है, T1 है. Same चीज़ है, हमें length ऐसे assign करनी है जिसको such that between S1 and T1, any path has length at least 1. Right? हर path की length कम से कम 1 होनी चाहिए. और जिन edges को हम length assign कर रहे हैं, वो इस तरह से length होनी चाहिए so that LEC is as small as possible. Right? If you think about it for a minute, where will you assign the edges, the lengths to the edges? Which edges will you assign a length to? You will take the minimum cut of this graph, the smallest capacity cut, and give all of those edges a length of a 1 and all other edges a length of a 0. Right? So this is just an extension of that idea. I'm not saying that length function has to be an integer length function. It does not have to be an integer length function. It is any length function that you want to use. अब मुझे बताइए कि इस example में what is the length I should have assigned to the edges such that what length should I assign to the edges such that between every S1 T1 S2 T2 and S3 T3 there is only a unique path in fact उसकी length 1 होनी चाहिए at least 1 होनी चाहिए. अब समझ आ गया. You are all wise now. Everything is half in this. No, that's not true. I'll tell you a story about that. Right? So if I assign half to every edge, then you can see that it meets those conditions. That every S1 T1, every path between S1 T1, every path between S2 T2, every path between S3 T3, and there is only a unique path that has length at least 1. Furthermore, what is the value of the objective function? What is the value of the objective function? If I assign half to everyone? 3 by 2. And it is equal to the maximum flow that I sent, right? You would have learned that at optimality, these are both the same. So if they are coming to be the same, then it's an optimal solution. Yes? And that is my answer to that question that was asked. How do I convince you that this flow is the maximum possible? How will I convince you that this flow is maximum possible now? By building a dual. By showing you a dual, by showing you a length function which assigns lengths to the edges in such a manner so that every shortest path, not every shortest path, every shortest path between the k pairs that are given to us is at least 1. And then the LECE value of that length function should be equal to what? The maximum flow. If you can show that, then that's your maximum flow. If you cannot show that, then that's not your maximum flow. So that's a certificate for a certain flow to be a maximum flow. Right? So maximum flow can be easily computed. You can just write a linear program. But multi-cut, that's NP. Right? You cannot compute the minimum multi-cut. What you can compute is this length function assignment to the edges. Right? So now here comes in the game of integrality. You can compute this. Right? This is, what is this saying? This is saying between every source and sink pair, the length of the path is at least 1. Suppose magically it happened that these lengths were all 0 or 1. Suppose you solve this linear program. I claim you can solve this linear program in polynomial, right? Suppose magically it happened that all these lengths were 0, 1. Then if I look at the edges which are at 1, what can I say about them? They form a multi-cut? Yes, why? Because if I remove those edges which are at a 1, what happens? Is there any path left between a source and a sink? No. Why? Because it should be at least 1. If there's a path left, then it is all zeros. Not possible. So, an integer solution to this is a multi-cut. If somehow I could get an integer solution to this linear program, I have a multi-cut. But even in this simple example, the optimum solution is not integer. Okay? Good. So now, what am I going to show you next? So you understood the linear programming formulation. I'm now going to talk about multi-cut on trees.
Can you please explain why it should be integer for this condition to hold?
Sorry?
Can you please explain why it should be integer again?
No, I'm not saying it should be integer.
For this to
I'm saying if it is integer, okay, so one step at a time. The requirement is that the lengths of every path be at least a 1. So if it is integer, you will never give any edge a length more than a 1. Right? Because the only requirement is to meet 1. Right? Why will you give some length 3 or 5 or 7? Right? After all, you are minimizing this and everything is non-negative. So integer means 0, 1. If I have an integer solution to this, then it's a 0, 1 solution. If I look at the edges which are at a 1, they form a multi-cut. That's all I've said. right? That's what you understood by the form multi-cut, that's all, right? So, pictorially, okay, yeah, so this is an important thing that I always do. So this is maximum multi-commodity flow. Is this green color visible at the back? Likely not, right? Sort of. Okay. So this is maximum multi-commodity flow, which is equal to minimum, I'm now putting in brackets, fractional multi-cut. What do I mean by fractional multi-cut? A multi-cut which is a solution to this linear program. Basically, it's assigning fractional values. It's as if I have distributed the cut across many places, right? So this equality, these are equal, and this follows from linear programming duality. The maximum flow is equal to the minimum fractional multi-cut, right? Now, so this is also maximum fractional multi-commodity. So we can talk of maximum integral flow. Suppose I wanted to send flow integrally in this graph, right? Then that will only be less than the maximum fractional flow. If you can send something integrally, you can also send the same thing fractionally. If you can send something fractionally, it's not necessarily that you can send it integrally. In this example, what's the maximum integral flow? Oh, okay, sorry. S1 T1, yeah. What's the maximum integral flow?
T2.
1. Right? You can only send one commodity integrally. After that, the game is over. So the maximum integral flow in this picture, so is only less than the maximum fractional flow, which is 3/2, right? So for this picture, this quantity is a 3/2, this quantity is a 1, and then what should we have here? Minimum multi-cut. And this, I need not say it here, but this means integral. Unless specified, it means integral. Right? By multi-cut, I mean a set of edges whose removal disconnects every pair. This is fractional multi-cut. Integral will only be larger. Yeah, because we are trying to minimize this quantity. So something that's an integral multi-cut is also a fractional multi-cut, but fractional could be even smaller. Here, same example. What's a fractional multi-cut? What's the value of the fractional multi-cut? What is the value of the fractional multi-cut? 3/2? Yes? 3/2? थोड़ा energy low लग रहा है? Yes. So this is 3/2 equals 3/2. What's the minimum integral cut? 2. Yeah. So just this example shows this picture here, that these quantities are different. The maximum fractional flow, fractionally जब हम बात कर रहे हैं, these are the same. Once you go integrally, maximum integer flow is going to be less than the maximum fractional flow. Minimum integral cut is going to be more than the minimum fractional cut. And what happens, and I hope to cover that fully in this class, is to show that this is the picture for trees. Right? For a tree, I'll just come to that question. So in trees, maximum integer flow is at least half of minimum multi-cut. Right? Basically, ये जो gap है, ये जो मेरे को यहाँ नहीं यहाँ बनाना चाहिए, ये जो gap है in a tree is at most 2. What does it mean to claim that this gap is at most 2? It actually implies many results. It means that this gap is at most 2, which means that I have a 2 approximation for multi-cut, which means that this gap is also at most 2, which means that I have a half approximation for integer flow, maximum integer flow. This is also an NPR problem.
Even on trees.
Sorry?
Even on trees.
even on trees. It's all on trees only, right? So this is for trees. And for general graphs, this is log k. Let me put, it's 4 log k at most for general graphs. Yeah. So these are what are called approximate, as you can imagine, these are called approximate max flow min cut theorems. Right? Min-max relations are central to optimization, combinatorial optimization, and they're, for many problems, their approximate versions are key to designing approximation algorithms. Right? So these are sort of the bedrock, these are the things on which a lot of approximation algorithms is built. Right? Not just, I'm not saying this particular result, but when you see min-max relations, that's the nice setting, and whenever you have an NP-hard problem, those will likely translate into some kind of approximate min-max relations. Okay, questions? There was a question, yeah.
So you said that max flow could be found easily.
Yes.
But its maximality, to show its maximality, we need to show that LP.
Yes.
But that itself is exponential in size.
No, वो मैंने यहाँ इस class के लिए I said कि वो मैंने exponential size LP बनाई. Can you formulate a smaller LP for this? Okay, if you had to formulate a smaller LP, a polynomial size LP for single commodity flow, can you do that? Remember, we define flow as a function on the edges. So all you need is variables on the edges, and you need to capture conservation, right, which is one constraint for every node, and you need to capture capacity, which is one constraint for every edge. So with number of variables equal to number of edges, and number of constraints equal to number of edges plus number of nodes, you can formulate the LP for one commodity. Now translating it into k commodities is not difficult, right? You just replicate that k times, one for each commodity. So short answer, you can formulate that linear program succinctly, and so you can solve it in polynomial time.
How are we exactly finding that max flow easily? Like what kind of algorithm?
Okay, so right now what I've told you is what's called is by solving the linear program. But max flow for single commodities, there's a lot of research on efficient algorithms. For multi-commodity flows, the only known methods are what is called, there's this class of methods called multiplicative update algorithms. And so actually I can tell you, it's a very simple algorithm. Right? It says you have a graph, multi commodity flow निकालना है आपको, तो आप कुछ सबको हर एज को एक लेंथ दे दो, राइट? वो लेंथ कहाँ से आ रही है? बेसिकली वो डुअल से आ रही है, राइट? इसलिए मैं वो टर्म लेंथ यूज कर रहा हूँ. हर एज को कुछ एक लेंथ दे दो, ठीक है? फिर शॉर्टेस्ट पाथ निकालो बिटवीन एनी पेयर, और उसमें फ्लो भेज दो. कितना फ्लो भेजोगे? जितना भी माना है, राइट? मे बी जितना ज़्यादा से ज़्यादा भेज सकते हो, विच इज द मिनिमम कैपेसिटी एज ऑन दैट पाथ, ठीक है? अब फिर हर एज की लेंथ इंक्रीज करो. कितने से इंक्रीज करोगे? इफ एन एज इज वेरी क्लोज टू इट्स कैपेसिटी, उसकी लेंथ लेट्स से डबल कर दी. बट इफ इट्स लिटिल फार फ्रॉम द कैपेसिटी, तो उसकी कम, राइट? द एग्जैक्ट फंक्शन यू कैन सी बाय रीडिंग द पेपर्स. सो यू इंक्रीज एवरी एज, द लेंथ ऑफ एवरी एज ऑन दिस पाथ, एंड नाउ यू रिपीट दिस प्रोसेस. फिर से एक शॉर्टेस्ट पाथ निकालो, राइट? तो क्या होगा? जिन एजेस के ऊपर ऑलरेडी बहुत सारा फ्लो जा रहा है, राइट, उनकी लेंथ बढ़ती जाएगी. जब उनकी लेंथ बढ़ती जाएगी तो सब्सिक्वेंट शॉर्टेस्ट पाथ जो आप निकाल रहे होगे उन पे वो एज नहीं आएगी, तो उनके ऊपर कम फ्लो और आएगा. तो जब ये हमारा प्रोसेस टर्मिनेट होगा तो हम ये नहीं कह रहे, वी आर नॉट सेइंग दैट एवरी एज हैज फ्लो लेस देन द कैपेसिटी, बट इट विल हैव फ्लो एट मोस्ट log times the capacity. So after that you'll just scale down all the flow by log and you'll get a feasible flow. Okay? So I'm not going to cover that. This is broadly the idea for computing this kind of flows, right? If you want a combinatorial algorithm, if you want, you're happy solving a linear program, then you would do that. Okay? More questions?
it hard to route two commodities even on trees or?
Okay, NP hardness for so NP hardness kicks in for 3.
Okay.
For 3 on even in this kind of a setting, what's called a multi-way cut. That's a problem for you guys in the. So you have 3 pairs of vertices. You have 3 vertices, and you want to send flow between any pair of them. Right. So that so you want a cut which separates all 3. So for k equals 3, multi-way cut is NP hard.
And the 2 approximation is for any commodities, any number of commodities.
But only on trees, right? So this is for trees. This is for general graphs. Okay. Good. Yeah.
What kind of rounding?
Sorry?
What kind of rounding algorithms are known for this type of issue? If you try to round, like what kind of approximation can you get?
Okay. What would you do to round this LP?
Yeah, it's not clear.
Yeah. So in fact, the log K is what's called a region growing idea. So I'll briefly give you an idea just so that you guys have a flavor for it, but I'll not be able to do it in full detail. So let me give you an idea of the rounding things. So here we'll use a rounding idea, but here we'll actually not, this is more a primal dual algorithm, right? We are not going to solve the linear program and then round it, okay? Okay, good. So let's take a tree. Okay, what's the simplest tree? The simplest tree is just a 1-level tree. Yes? And I'm going to argue that even for this tree, you can't do better than 2. Right? So let's say this is S1 T1, this is S2 T2, this is S3 T3, this is S4 T4. Right? मैं arbitrary ग्राफ हूँ, मैंने कुछ सोचा नहीं ये सब, ठीक है? Oh, S5 T6 with S5 T5. Right? And let's say all these capacities are 1. Okay? Yeah? What's the minimum multi-cut in this? Basically, I need to remove some edges. Yes, that would be a multi-cut, so that every pair gets separated. Okay. Let me make a graph on these 5 nodes. What edges do you think I'll put in? SITI, good. S1 T1, S2 T2, S3 T3, S4 T4. Okay, S4 T4 के बीच में already S2 T2 भी था. हो सकती हैं, multiple हो सकता है, but हम इसको अभी नहीं करते. S T4 को यहाँ डाल देते हैं. तो S4 T4 यहाँ हो गया और S5 T5 यहाँ हो गया. Okay, ये मैंने ग्राफ बनाया. If I remove, so let's take a multi-cut here. Okay, what's a multi-cut here? अगर suppose मैंने ये वाली edge हटाई होती, तो 1 और 3 दोनों गए. अभी मुझे 2 और 4 को हैंडल करना है. ये edge हटा दी. और 5 को और हैंडल करना है. Let's say ये edge हटा दी. ठीक है? Which means ये वाला vertex उठाया, ये वाला vertex उठाया, और ये vertex लिया. What do you think? What can you say about if this is a multi-cut here? What is this in this? Vertex cover. Very good. Everyone sees it? Conversely, if you have a vertex cover here, you have a multi-cut here. What does that tell me? That tells me that इसका 2 approximations से ज़्यादा नहीं हो सकता unless आप vertex cover को improve करो. ठीक है? Even for something as simple as this. Okay. So, what's my algorithm going to look like? Now, I'll straight jump into the algorithm. So, I'm going to root the tree at an arbitrary vertex. कोई भी एक वर्टेक्स लिया उसको रूट बना लिया. Okay, and then what I'm going to do is I'm going to go bottom up in this tree. And just look at this. Look at this subproblem. Let's say this is the bottommost. Is this the bottommost level? My levels are a bit off, but okay, let's say this is the bottommost level. Suppose there was an S1 and a T1 here. Okay? And maybe there was S2 here and no, I should not take it, or let's put T2 here. And let's put S3 here and T3 here. S4, T4, S5, T5, S6, T6, S7, T7. That should suffice. So अभी मैं bottom इस पे level पे गया और मैं जितना ज़्यादा flow भेज सकता हूँ S1 T1 path पे. The maximum amount of flow that I can send on S1 T1, I send it. What do you think is the maximum I can send? The capacity, right? All edges have some capacities on them. Let's say this was 3, this was 5. I can send 3 units of flow. I send 3 units of flow. And now this edge is tight for me. So I mark it as tight. And I include it into my multi-cut. Looks good for now, right? I have 3 units of flow. I have a multi-cut of size 3. Of course, this is not my final solution because this multi-cut is not separating every pair. It's only right now separating this pair. I'll continue. I'll go up in the tree. Maybe this was the next level. Let's say these were 2, 3, 4, 1. S5 T5 पे मैं कितना फ्लो भेज सकता हूँ? 1 यूनिट भेज सकता हूँ और फिर ये एज टाइट हो गई मेरी. ठीक है? फिर S4 T4 पे मैं कितना भेज सकता हूँ? 2 यूनिट्स भेज सकता हूँ और फिर ये वाली एज टाइट हो गई. ओके, यहाँ पे S8 T8 डाल देते हैं. So all I'm trying to do is I'm just trying to take any pair, जिसके both the nodes, the source and the sink are within here, right? And I send as much flow as I can for that. So I did that, and now here I can also send more flow for S8 T8. How much flow can I send for S8 T8? Huh? 1. Good. Someone is right because हमने S4 T4 का 2 units भेजा था, right? So इसका 2 units use up हो गया. So I can only send 1 more unit for S8 T8, and after that this edge will become tight, right? So I include all these 3 edges into my multi-cut, and I just go up 1 level after this, right? So maybe next level is I go up here. Actually, yeah. So I think this and this are the same level. So then I would route flow between S2 and T2, right? How much flow will I be able to route? Whatever is the minimum capacity edge on this path. Maybe this is the minimum capacity edge on this path. It is 2. So I route 2 units of flow and I do. Right? So as you can see, what am I doing? I'm actually building an integer flow, and I'm also building a multi-cut. Right? I'm building both an integer flow and a multi-cut. And I keep doing this as I go up the tree. Why am I doing it in this bottom-up manner? Can someone give me some insights on that?
No use going up for the under subtree, the flow will not, both the SI and TI are under subtree.
Inside, yeah.
It won't go beyond the...
Would it have made sense to take some path which is going all the way up and route there? Like you can imagine if I took some very long path, it will stop a lot of other paths, right? It will obstruct a lot of other paths. So I'm trying to, do some low level things first, and only then I move higher level, right? So this is just to try to maximize the flow I can send in this way. Okay, so we build this thing, and then, so this is phase 1. So phase 1, route flow. Let me mention this is integral flow. We are assuming edge capacities are all integral, right? We can always round them down to make it integral. Route integral flow and pick edges in multi-cut. Now phase 2, delete unnecessary edges from multi-cut. Okay. Did you see reverse delete? Did Did you do primal dual algorithm and you saw reverse delete in that? Right? Okay. No worries. Okay, what does it mean remove unnecessary edges? Okay, by the way, you should be convinced at this point that every pair is separated if I just look at these edges. Why? Because हर पेयर के लिए मैंने फ्लोर आउट किया जितना ज़्यादा से हो सकता था और एक एज उस पाथ पे टाइट हो गई मतलब फ्लो इक्वल्स कैपेसिटी, टोटल फ्लो इक्वल्स कैपेसिटी, एंड फिर उस एज को मैंने हटा दिया और उसको मैंने मल्टीकट में डाल दिया. So if I just look at the set of edges that I have in the multicut, they are actually a multicut. They are a feasible multicut. Then separate every pair. Now question is, why is this multicut just 2 times the flow that I wrote it? Can this multicut be much larger? Okay, let's see if I can give you an example. Right. So suppose I have S1 T1 here, S2 T2 here. Okay, and let's say we picked, let's say this is capacity 3, this is capacity 5, this is capacity 4, and this is capacity 3. Okay, so what did we say? We'll go in the bottom up manner. When यहाँ पे there is nothing that we can do, we come here and then we will route, let's say, S1 T1 flow. How much S1 T1 flow can I route? 3 units, and this edge goes tight. Yes? Then what I'll do is I'll go and route S2 T2. How much can I route? 2 units. Everyone is with me? And which edge goes tight? This edge goes tight. Yes? Right? 2 units from here to here. This is 3, this is 2, this edge goes tight. Right. Now, as you can see, are both of these edges necessary? Is one of these edges unnecessary? Which edge is unnecessary? Huh? S1, S2 is not needed. Okay? S1, S2 is not needed. Why? Because, well, this is doing the job of S1, of separating S1, T1 as well. Yeah, so S1, T2. So in the second phase, I am going to go down, which stops from the top. And I am going to consider edges in the reverse order in which they went tight. Right? So, jo edge last, the edge which went tight at the end, I'll ask myself, can I drop this edge? When can I drop an edge? If by dropping the edge, it still remains a multicut. The remaining set of edges still forms a multicut, then I can drop that edge. Right? As simple as that. So if I can drop that edge, I drop that edge. Otherwise, I keep it. But I'll do this in the reverse order. Okay? So we do that, we'll drop this edge. So when I'm trying to drop this edge, so this is the last edge that went tight. When I try to drop this edge, will I be able to drop it? No. Why? Because this is separating S2 T2. I cannot drop it. So I'll keep this. When I come to this edge, I'll ask myself that question again. Can I drop this? And this, yes, you can drop it, because even by dropping it, this thing is a multicut. Okay? So that's what we do. And the claim we prove is claim on any SI-TI path, there are at most 2 edges in the multicut. Okay. What does this mean? It basically means the following. Yeah.
Why do
give some intuition why you have to. We don't want to go closer, will go bottom up. But now why do we do top down? When we are deleting.
Okay, I'll have to come up with an example which I will not be able to do right now. But yeah, as far as I remember, reverse delete is needed, right? That you really need to go in the reverse order, right? Okay, so let me.
Will show up in the analysis.
I'm not going to be able to do the analysis. I have 10 minutes left, so I'll encourage you to read the paper, right? Okay, so what is it? So important thing is for you to understand what is the claim being made. Suppose this is SITI, right? And remember, one edge of this path is in the multi-cut, right? Because reverse delete ke baad bhi, even is phase 2 ke baad, even after this, the set of edges that I am left with is a feasible multi-cut, right? Because the feasibility I am carrying it through. I drop an edge only if it remains feasible multi-cut. So which means that some edge on this path is in the multi-cut. What this claim is saying is that, suppose this edge is in the multi-cut. Actually, this claim is not saying that. It's saying at most 2 edges can be on the multi-cut. At most 2 edges of this path can be on the multi-cut. And what this is not saying is that those 2 edges, at most one can be on this part and one can be on this part. What are these parts? Basically the least common ancestor of these 2 vertices, right? On this ascending part and the descending part, or both are ascending. So on this part from the terminal to the LCA, they can be at most 1 edge. And so this picture is okay, right? But you cannot have 2 edges here, right? This statement would have allowed 2 here and 0 here. That's not also there. At most 1. I could write it, but this is sufficient to argue a 2 approximation, or it's sufficient to argue this. Why? Remember, the total capacity of the edges in the multi-cut is equal to the capacity of this edge is equal to the total flow going through it. The capacity of this edge is equal to the flow going through it. Yeah. So why is the total capacity of all the multi-cut edges not equal to the total flow? Because some flow is getting counted, but at most twice. Yes? Each flow can be counted at most 2 times towards the capacity of the multi-cut. Right? 1 unit of flow can be contributing to 2 units of the capacity of the multi-cut. So the multi-cut is at most 2 times the flow we plotted. That's it. That's a proof. So the only claim is this, and this follows from the way we have done the reverse delete. Right? If there were multiple edges here, then you would argue that, well, one of these is going to get dropped in this particular step. Okay? It's not a very difficult argument, it's a half-page proof, but let me instead talk about the general graph result. Yeah.
When you're coming down, how would you decide whether to drop? When you're doing the reverse delete, when you see the first edge, how do you decide whether to delete it or not?
Well, you delete it. If it remains a multi-cut, then you drop it. If it doesn't remain a multi-cut, you keep it. As simple as that.
When deleting it, do we assume that the other edges that
Yes.
are yet to delete? Okay.
Yeah, no. So you start with you have your set of edges that you built up. That's your current set. And for each edge, you're saying, is this unnecessary? Basically, keep that in mind, the word unnecessary. And the edges that are being considered in a specific order. That's all I'm saying. If it is unnecessary, which basically means even if I don't include it in my multi-cut, the rest is still a multi-cut, right? You can just think of it as minimality, right? Is this cut minimal? If it is, throw that edge away. That's it.
That can prove this.
That can prove this. Okay? Okay. Good. So now let me tell you about, again, the proof I will not be able to do, or I'll give you an idea of the proof. Question? Yeah.
So when those 2 states is taken in our multi-cut is when we are giving a SITI flow and it is saturating those 2 edges, right?
Yeah, so like this example, right? So here I pick this edge, because I sent this flow, and this edge had less capacity than this, so this got tight. And then I picked this edge because I sent this flow.
Yeah.
So on this path, as you can see, there are two edges which are tight.
So why not we immediately delete one of these two edges chosen in the right example?
Or immediately delete, as in the single phase when we're going up itself?
Yeah.
We can do it. Yeah, we can do those changes. It's just to keep the algorithm simple, right? That in the first phase you are just collecting edges, and in the second phase you are saying, okay, everything that is not needed, let's just throw it in. Right? That's just to simplify the description. It would make it more complex doing it that way, but perhaps it can be done. Okay, so I'm now for general graphs. What happens for multi-cut and general graphs? So here we are going to solve the linear program, solve the dual LP. The dual linear program, which I've erased now, but you remember, is an assignment of lengths to the edges such that between every source and pair, the shortest path has length at least one. Yeah? Okay, then what I'm going to do is, I'm going to take some SI, let's say, anyone, maybe I take S1. And I am going to grow a region around it. So the way to think of it is, I'm growing a ball. Suppose this ball has a radius r. Then what are the vertices inside the ball? What do you think should be the vertices inside this ball? All those which are at a distance of less than r from S1. And how are distances computed? Using the length function that is coming from here. So BS1R equals set of vertices with distance less than or equal to r under length function L. Okay? Then we'll also talk of the cut associated with this. So C of S1 comma R equals B S1 comma R comma B S1 comma R complement. What is the same? Basically this set of vertices and the remainder. And so the cut is basically all the edges that are going out. Okay? This is the cut. And keep growing till C S comma R. Okay, abuse of notation, C S comma R is this cut, is also capacity of this cut. Okay, I'm going to use the same CS1 comma R, S1 comma R, till CS1 comma R is less than or equal to 4 log K times volume of S1 comma R. Okay, what is volume of S1 comma R? So I'm going to associate a volume with this ball, right? And the volume that I'm going to associate is that for every edge which is inside, completely inside, I'm going to count its LECE. So just think of volume of this ball as summation LECE. E belongs to the ball. E belongs to the ball मतलब उसके दोनों एंड पॉइंट अंदर है. ये ज़्यादा समझ में नहीं आ रहा है, ठीक है? Right? So I'm associating. So there is this ball that you can understand, right? It's basically all vertices which are at a distance of r from S1. Okay? And we are talking of a certain quantity. Remember, this L is the optimum solution of the dual LP. So the dual LP, remember, is minimizing summation LECE. Yeah. So I'm going to ask what is the total, if I look at the edges which are sitting inside, what is the LECE value for them? And I'm going to call that the volume of them. Right? And I am going to grow this ball till I can find, till I can reach a point R, such that the volume inside this ball, sorry, the cut associated with this ball is less than 4 log K times the volume inside this ball. Okay. Thoda sa or we'll make things nastier by saying what about the volume of this edge? Some part of it is inside, so whatever part of it is inside, we will take that into the volume. So what does that mean? We can think of it as, okay, this part is inside. So some way of associating this part with this volume we will do.
The ball growing is a smooth process, or is it done by adding vertices?
It's done by adding vertices, but I'm thinking of it as a smooth process right now. But the right thing would be to discretize it.
And are you worried about including TI in the ball, or
Sorry?
Would you worry about TI coming in? I mean, you want this to be a cut.
Yeah.
So, are you worried about hitting the other terminals?
Yeah, so we would of course be worried about that, yes, certainly. So this ball, okay, so now intuitively, if this cut is large, right, so we keep growing the ball till the cut is large, while the cut is large, not till, while the cut is large. So if this cut is large, then what does that mean? That when I grow the ball, its volume will increase even more, right? And if the cut remains large, then the volume keeps increasing by this log K factor. Yeah? Now this 4 log K has been chosen so that within a distance of a half, its volume will become equal to, its volume will, okay, so thoda sa aur main karunga, will increase by a factor of K. Yeah? So K is the number of terminals, number of pairs. Okay? So this volume, I'm going to define it as this plus some F by K. This quantity is F, right? The value of the maximum flow. So note that the volume of this ball initially, so we are thinking of, we associate a volume with this vertex that we started with, and we are associating a volume of F by K with it. And what is the total volume that I have available in the graph? All edges put together. All edges put together, the volume is just F. Yes? So I started with a volume of F by K. The total volume is, let's say, F or F plus F by K if you also want to include the volume of that vertex. And so I cannot grow this ball too much. Because if I grow this ball too much, the total volume will become equal to K. Will become equal to F. I started with a volume of F by K. If I am growing at this rate of log K with every increase in radius, then within a constant increase of radius, and I'm doing a bit of hand waving because I'm already out of time. So so what one can argue with this kind of a process is that this ball will not grow to more than a half radius. Right? Within a half radius, if it grew to a half radius, then already the whole graph will be inside. Right? Because the total volume will then have to be the starting volume times K, which is the entire volume of the graph. Why half radius is good? That comes to Neil Dhara's question. If the radius is only half, then T1 cannot be inside. Because S1 and T1 are at least 1 apart. So I'm going to take this and I'm going to call it a cut. I'm going to include all of these edges into the cut. Why is that good? The total capacity of these edges is log K times the volume inside. Why is that good? Because after this, I took these edges in the cut and I'm going to repeat from another S7 that is sitting outside maybe. I'm going to grow another ball. I'm going to repeat the same thing. this cut is going to be less than log k times the volume inside. And then I'm going to have another cut. And the capacity of this cut is going to be less than log k times the volume inside. So what is the total capacity of all the cuts? Log k times the total volume which is inside their balls. Right? And the total volume inside those balls is at most F, which is our dual. So you get that the capacity of the cut is less than order log k times F. What is F? F is this quantity. So you found a minimum multi-cut. Actually no, this is not, yeah, this is F. Oh, sorry, ये मैंने गलत कर दिया. ये होना चाहिए.
Why isn't an edge counted twice or more?
Why is an edge not counted twice or more? Because I remove this part. So it will get counted at most twice, but not more. Yeah? So when I have this ball, I remove all these vertices. So, yeah? No. So that 4 takes care of everything. As far as I remember, the final bound is something like 4 log k plus 1. Right? So that's why I kept it 4. Right? So there is a little bit of wiggle room. So it's yeah. For now, you can just say order log k. Okay? So what's the key idea? What's the key thing that you need to remember here? Is so what are we doing here? We are sort of trying to charge the cost of this cut, the capacity of this cut, to the dual value. Right? The dual value we have. And the dual value can be associated with individual edges. Right? Which is why we define this notion of a volume. Right? And we are trying to charge this capacity to the total volume of edges inside this. Right? And if this capacity is much more than this volume, fine, this is not a good cut to take. But this cannot repeat very often. Because if the capacity is always larger than the volume, right, and that's happening at every step, then that means that the volume is growing exponentially. Right? And within the log k steps, it will become more than the entire graph's volume. So you'll only be able to go for the log k steps. Okay. So again, the math for this is, so all of this is covered very well in the book by Schmois and Williamson. Right? I'm sure all of you have access to that book. This is called Design of Approximation Algorithms. This should also be covered well in the book by Vijay Vazirani. What? Approximation, I think. I think that's just called Approximation Algorithms. And if you are really in a bad mood and you want to read the papers, then this is a series of 2 papers. Garg Vazirani Yanakakis. This is from Stock 92. This is from ICAP 93. This is the tree paper, and this is this general graph paper. Okay? A little bit of advertisement. Okay. But I think this is now fairly standard material and has been covered very well in the David Williamson book. So just look at that. Okay, thank you.